Okay, so let's do the Otto cycle. So the Otto cycle, just as kind of a general introduction to what the Otto cycle is it represents the ideal cycle for a spark ignition engine. That's a gasoline engine. Okay? So we have a gasoline engine, and it's described by a 4-step process. And it's described by isentropic compression from bottom dead center to top dead center, constant volume heat addition, isentropic expansion from top dead center, which is the minimum volume, to bottom dead center, which is the maximum volume of our piston system, and then constant volume with heat rejection. So I describe it here, and I have A and B, sketch the PV and TS diagrams. So here are my PV and TS diagrams, and I'm going to be at state 1. And I need to just choose which one I'm going to try to do first. And the rule of thumb is PV is usually easier than TS. Carnot cycle is the violation to that. But there's other cycles where TS is easier too. So I just want to start. I need to put a dot somewhere on this graph. So I always recommend what was suggested, bottom right. And if you notice that you start going down below, then you probably want to go upper right likewise. So we'll just start state 1. I'm at a given specific volume, and I'm at a given pressure, P1, V1, and I have isentropic compression from bottom dead center, which I mentioned is Vmax, so I got compression. So given that I have compression, I know I'm going in this direction. It's isentropic, which doesn't mean it's constant pressure, but I can just write out the ideal gas law, and I can see that as I compress a gas, typically my pressure is going to go up unless I remove a lot of heat. Yes? Question?
Isentropic always referred to constant entropy, right?
Isentropic defines a process where delta S is equal to 0. So if I look at a TS diagram, I'm just going to draw this state, and I have an isentropic process, I know that I have to be on a line. I have to be, because delta S doesn't change. And if I have a line, what's the area under the curve for a straight line? 0. So isentropic, delta S equals 0. There's no net heat in, no net heat out. Adiabatic. So I have a process like this. I have compression from bottom dead center to top dead center. So this, I know I'm going to go to some V minimum. So these are going to be my extremes. Isentropic compression. And then I can just say that I get some intermediate increase in pressure to P2. So I get something that looks like this. Okay? And then I have constant volume heat addition. So if it's constant volume heat addition, again I can write P V equals M R gas T. Constant volume, so P heat addition, temperature increases, constant volume, P increases as T increases. I add heat, I heat up my system, I increase its temperature, so I know my pressure goes up to 3. And in this case, I have Qn. And then isentropic expansion from top dead center to bottom dead center. So I know I have an isentropic process. So I end up right here. And then constant volume with heat rejection. So this is my PV diagram for my Otto cycle. Ideal Otto cycle. And I just want, all I really need to do, this is pretty straightforward, it's constant pressure with heat addition, so I just want to write isentropic and isentropic. And I could put expansion there. And again, I have a clockwise cycle, so I know that this is work net out. So now let's do the TS diagram. I have isentropic compression from top dead center to bottom dead center. I go to 1 to 2. I have constant volume heat addition. So now I could write out the TDS relationship again. So constant volume heat addition. What should happen to the temperature? I'm adding heat. Isentropic expansion. So S12, S34, isentropic expansion, isentropic compression. In this case, I have QL, which is Q out, and in this case, I have QN, which equals QH. And it is clockwise, so the area is Q net in. So the next part of the problem is derive the thermal efficiency for the Otto cycle in terms of T1, T2, T3, and T4. So I probably should put my labels there. So let's do part C. Thermal efficiency, Otto, which is equal to the work net out over QH, which is equal to work net out over QN, which is equal to 1 minus QL over QH, where that represents the heat out, the heat in. And the same as before, QL and QH can get via first or second law analysis. So if I look at this, QL, Q out, that's from 4 to 1, I have heat rejection. Constant volume, heat rejection. Four to 1, change in temperature, change in entropy, heat rejection. So based on the fact that this is constant volume heat rejection, what is the area under the curve? So I'm already, it's implying that Remember on the TS diagram, we had something where there was 0 between the state, and so the second law was better. In this case, we have no work out or work in. So let's use first law. QL, and of course, first law QL is 4 to 1. So let's write out the first law. From 4 to 1, I have Qn plus work in plus energy associated with mass in 4 to 1 minus Q out plus work out plus energy associated with mass out. Again, that's this process, 4 to 1, equals the change in internal energy from state 4 to state 1, which is U1 minus U4. So all I did here is wrote out the full energy balance from two thermodynamic states. And so let's simplify it. What is my heat in from 1 to 4? Heat in. What is my heat in from 1 to 4? What is my work in 1 to 4? What is my mass in? What is my heat out? QL. What is my work out? What is my mass out? So I got minus QL is equal to U1 minus U4. Or QL is equal to U4 minus U1. And this is a constant volume process. So if you remember, the partial of U with respect to T at constant V is equal to CV. So delta U is equal to CV delta T. So using these two, what do I get? QL is equal to my mass times the heat capacity at constant volume times the temperature at T4 minus the temperature at T1. So let's do this part. So let's do QH, first law. And QH, first law, is 2 to 3. So let's write out the full energy balance. Let's just simplify it for the time being by looking at this one above. And so what is my work in from 2 to 3? No work in. What is my heat in? So I have QH. What is my mass in? From 2 to 3, 0. So this is all my in 2 to 3 minus my heat out. There's no heat out. There's no work out. There's no mass out. Equals the change in internal energy from state 3 to state 2, which is U3 minus U2, which means that I got QH is equal to U3 minus U2. And then I know that the partial of U with respect to T at constant volume is equal to CV delta T. Remember, this is small u. That's why that mass came in there earlier. So I end up getting QH is equal to mass times the specific heat at constant volume, T3 minus T2. So I did first law analysis between the two states, energy balance between the two states to determine my heat in, my heat out. So if I want to do the thermal efficiency, Otto is equal to 1 minus QH, or QL over QH, which equals 1 minus MC CV T4 minus T1 over M CV T3 minus T2. These cancel out, which means that the thermal efficiency for my Otto cycle is 1 minus T4 minus T1 over T3 minus T2. Okay? So what I'll probably do is so did everybody leave or did some new students come in?
They're waiting for
Okay. So we'll have to stop it and maybe I'll find another classroom we can go to
Like later, as in right now, or on another day?
right now. Unless I don't, it's going to be really hard to find